So barring any questions, I'm going to ask you guys questions. If you had to define a buffer, just take a moment for yourself and define the term buffer. A buffer is a solution containing equal concentrations or close to equal concentrations of a weak acid and its conjugate base. And one of those is going to be a salt. The pH, and this is, it maintains pH at a relatively constant value. Okay, so if I were to say, I'm just going to pull something up here on my other computer. Oh, 12. There we go. Okay, so I'm just going to put up a couple questions and you guys can try answering them. A 2-liter solution contains 1 mole of weak acid, H3PO4, and 1 mole of the salt, Na, H2PO4. Write an equation that represents this equilibrium. Okay, try that for yourself. So there's 2 ways that you could have written it. You would have H3PO4, and you could just have it in equilibrium with H plus, and H2PO4 minus, or you could have written it as H3PO4 plus H2O in equilibrium with H3O plus H2PO4 minus. All right, second part of this question. What happens to the concentration of H3PO4 and to the pH when a small amount of, let me just make sure I want to use this compound here. Yeah, okay. Strontium hydroxide, SrOH2, is added to this buffer. So you can think that through. So we are looking for whether the H3O plus increases or decreases or stays the same. We are looking for if the pH increases or decreases or stays the same. So if we are looking at our equilibrium here, if we add some SrOH2, that means we are adding OH minus, which is going to react with the H3O plus. And that means our concentration of H3O plus is going to decrease, which will shift the equilibrium to the right. Therefore, the concentration of H3PO4 is going to decrease. Now, to get at what happens to pH, we need to look at what's happening to the H3O plus. So the concentration of H3O plus initially decreases, right? Because we added that OH minus and it reacted with the H3O plus. So H3O plus initially decreases, but then it increases again as the system shifts to the right. Does it get back up to its original level? Anyone else want to weigh in on that? Does the hydrogen concentration get back to its original level? No, just Deborah? Okay, thank you, Deborah. Yeah, the answer is no. Okay, it's going to, if we have our graph here, we have our hydrogen ion concentration, or H3O plus. We add our hydroxide and it drops dramatically, okay? However, then the system shifts and starts making more H3O plus, but like all other equilibrium systems, it never quite gets back to its original. So the concentration of hydronium will end up lower than it was before, but not by a lot. Okay, and so that means that our pH, is pH going to be higher or lower than before? If our hydronium is higher than before, or sorry, lower than before, is the pH higher or lower than before? Okay, this is always tricky. Remember that pH, if you have a low pH, say less than 7, that is acidic, okay? And that means that if it's acidic, that means the concentration of hydrogen is, whoops, I'm mixing two combinations there. The hydronium concentration is higher. So the higher the hydronium, the lower the pH. So if the hydronium is lower than before, then the pH is going to be higher than before, okay? And so the pH is going to be higher than before but only by a tiny amount. Okie dokie. Let's see. Here's another question. Why is the action of a buffer limited? Ooh. Why is the action of a buffer limited? What on earth does that mean? It means, why is there a capacity to the buffer? Why does it stop working all of a sudden? Why is there a maximum capacity of added acid or base before the buffer stops working? Things can run out. So if we have our just any old generic weak acid, right? And A minus, and let's just say we had 1 mole of the A minus. If I added 2 moles of HCl, which would give us 2 moles of H plus, we would be able to react 1 mole of it, right? But then we would run out for the rest of it. Okay, so you would have 1 mole of the H left over and it wouldn't be buffering anymore. Very nice. Okay, let's try another one here. What chemical could you add to 1.0 molar hydrofluoric acid, fluoric acid, HF, to prepare a buffer solution? Yeah, we can add its conjugate base as a salt. So we're going to add its conjugate base as a salt. And Jason, you're absolutely correct. That is going to be NaF. That would be any alkali metal salt of fluoride. So the conjugate base, F minus, can be added as a salt. Maya, I wanted to say that NaOH actually will kind of work, but it's a little bit complicated. So what you could do, and this is sort of getting into what will happen in a titration and what we'll be getting into probably next week. Let's say that we start with our 1 molar HF. Okay, so initially we have 1 molar of our HF, and to that we are going to add some NaOH. Okay, could you guys please predict what happens for yourself? You can write it down and just write done when you're done. What's going to be the product of that reaction? Yep, we're going to end up with NaF plus H2O. Is that going to be a one-way arrow or an equilibrium arrow? let's consider the two things that we have here. We have HF, and HF is a weak acid. What kind of a base is NaOH? Strong or weak? Yeah, it is strong. So what's going to happen is NaOH is going to dissociate completely, and it's going to produce OH minus ions. Now, anytime an OH minus ion sees an H plus anywhere, it's going to grab it and form water. And even if that H plus is attached to a fluoride, the hydroxide will grab it and it will make water. Okay, so essentially what's happening is the hydroxide from the NaOH is ripping all of the protons off of HF. And so this actually will be a one-way arrow. As long as one of the reactants is strong, you're not going to get an equilibrium. Okay, as long as one of the reactants is strong, whoops, I can't spell. The reaction will go to completion. This is again going to become important when we start getting into titrations. Okay. So now I've written in my space where I was going to do my ICF table. So I'm going to write it again. Ah, there we go. Why is there that circle? Go away, circle. Or at least move up there. All right, that's good. Okay, so we have HF plus NaOH, and because the NaOH is strong, that is going to drive this reaction to completion. One-way arrow gives us NaF plus H2O. And if we start with, if we initially have 1 molar of the HF, and then say to that solution, we add, we'll just add it as a solid, so we're not mucking about with our volume and changing concentrations, diluting things. We're going to add enough solid NaOH so that we have 0.5 molar, okay? And that is at the beginning of the reaction. We have 1 molar HF and 0.5 molar NaOH, and the reaction hasn't started yet, so we're going to have none of our product, okay? Now, this reaction is going to go to completion. So what that means is that all of the NaOH is going to react because it is the limiting reactant. We're going to run out of it first, okay? And so we'll end up with 0 molar NaOH, okay? The HF, they react in a 1-to-1 fashion. Doesn't water not have a concentration? Oh, yeah, I should get rid of that. Thank you. There we go. And so HF is also going to react in the same fashion, minus 0.5 molar, 1-to-1. And so we will end up with 0.5 molar. And then finally, our NaF, it's still 1-to-1 to 1. And so this starts at 0, but it goes up by 0.5 molar. And so we'll end up with 0.5 molar here. So what that means is that we have 0.5 molar HF, and we have 0.5 molar F minus. And I now have equal, relatively large concentrations of the weak acid and its conjugate base. And if I have equal, relatively large concentrations of the weak acid and its conjugate base, what do we have? What kind of a solution is that? Yeah, it is a buffer, okay? Because if you go back to our original definition there at the top, where did it go? Oh, a solution containing equal or close to equal concentrations of a weak acid and its conjugate base. Oh, look at that. So if you have a strong base and it neutralizes a weak acid, when you have neutralized half of the acid, right? Half of the acid has been neutralized and half of it has been turned into the conjugate base. So when half of the acid has been neutralized and turned into its conjugate base, you're going to have a lovely buffer solution.